Algebra. Today is your first video lesson from home, and while I hope it feels the most like class that I can make it feel for you, remember that you can't stop me, obviously, during the video and ask me questions like you would in class. So times to ask questions would be whenever you want through email or Remind, and also to, obviously you can't stay after school, but we're doing those extra help Zoom office hours, and those codes for Zoom can be found in your email before those office hours, and those are posted on our math website. They'll always be updated. If you have any questions, I'll reach out, email me. I'm here to help. I want to help. I know this is so hard for everybody. So for today, we're learning about exponential growth and decay, and you guys all did an awesome job looking into those investigations last week. With the growth, you guys did the rectangles growing per amount of folds, and decay, hopefully you played the mammoth game with the virtual dice, and then you looked into how rich, who was it, Jill and Jack, maybe Jack and Jill's parents, they were super rich, so hopefully you figured out that exponential growth model was the one that you would want to choose. You'd want to go with Jill there, but you guys all did a great job with those. So let's go ahead and get started and take a more formal look at what exponential growth and decay are. So this is going to be our base formula for exponential growth and decay. And typically if we were in class, we would look at a graphing calculator. I'd have you guys kind of play around and kind of figure out on your own what these letters mean. But for today, I have it pulled up on my computer with, this is called Desmos graphing calculator, and you can get to it yourself. It's listed in the Google form if you wanted to try it. And I have listed out 6 different exponential functions. And here it is in color. I can post this as well. This is in color, so you can kind of match the color to what's going on over here. On your notes, if you printed it, it's probably not in color. I tried to label it with text boxes for you, so hopefully that helped. So basically, the introduction for today, and it'll ask you to do it on the Google form tomorrow, we're just looking for what happens when we change these numbers over here, what's happening to our graph. So most basic here is the 2, the 3, the -2, and then repeat it again over here. That number is going to tell us, and you'd be discovering this in class, but I'm going to tell you here, and you can check it out on your sheet as well. That number is going to tell us the initial value. It's going to tell us the y-intercept of the equation. So that is what that is, and we'll talk about that in a little bit more. What is in the parentheses, just for today, we don't need to look at it too much. We're just looking, these first 3 equations have values that are bigger than 1. So those are going to be growth equations. Whereas these 3 values, they're all a half, are less than 1. So those are going to be decay equations. And then one more thing I wanted you to look at is when we have a negative initial value, those are the green and the second red equation here. Those are going to be below the x-axis. So that's a super basic overview. It's going to be asking you to match a graph to an equation tomorrow when you practice. So let me know if you have any questions with that. This would just be in class. It would be kind of like an experiment on your own with a partner looking into it. We will look more into how to graph later in the week. So next I'm actually going to have you drop down way to the bottom of your notes if you have them. By the way, if you don't have your notes with you, you can just follow along and watch and kind of sketch notes out on a scrap sheet of paper. That's totally fine if you don't have a printer. So I'm going to come back up here. I have you on the bottom right now, the bottom left of your exponential growth and decay notes. And this is your exponential growth equation. So in orange, I have what the equation is for you. And then in that teal color on the outside, I've labeled what each part of the equation means. So if you're taking notes, maybe pause your screen so you can jot it all down. But what we talked, and we just mentioned this a little bit before, the initial value is going to be that A value up front. R stands for the rate. The exponent up here, X for the exponent, is going to be time intervals. And then this entire parenthesis is going to be our growth factor. And it's the same exact thing for decay as well, so you can pause it again if you wanted to take those notes for the decay box, except this is a decay factor instead of a growth factor in the parenthesis. So that is basically what we have. And I'm going to have you go back up, I'm sorry I'm jumping around a little bit, to the 3 bullets that you have right above those boxes. It says exponential functions each will have a line. It gets very close to, but never touches or crosses the x-axis. So that line's going to be called, or that part of the graph is going to be called an asymptote. I will spell it out for you in a second. And you can't really tell on my computer here, I guess. It looks like it's touching the x-axis. When this line comes down and gets close to the x-axis, it actually never, ever, ever touches. Technically, you can break something in half as many times as you want. You could do it an infinite amount of times. Now, there are constraints in real life things, like you learned with the mammoth game. Like sometimes all your mammoths died out. I talked to a few of you. It's okay if it was 0. But with the mathematical formula, that will never happen. Just like you can double something forever and ever and ever, and it will always continue to grow. So this is never going to touch this x-axis ever, no matter which equation we plug in. So that's called an asymptote, and you spell it A-S-Y-M-P-T-O-T-E. I can show you up here as well. So I filled my notes in already. So that's called an asymptote. And when a quantity grows exponentially, that's called exponential growth. And when it decays exponentially, it's exponential decay. So now let's get into what these look like a little bit more. Over here, it's asking if it represents growth or decay. I'm just putting my computer down. It asks if it represents growth or decay, and it asks us to kind of pick out what's going on with it. So here with this equation, I have my initial value of 4, and I have 1.5 in the parentheses. Now that 1.5 tells me it's going to be growth. And I know it's going to be growth because 1.5 is greater than 1. Now the rate here, I'm actually going to jump to the factor. The factor is easiest. The factor is what's in the entire parenthesis. Well, the entire parenthesis here is 1.5, so that's my factor. And the rate here, when we did our equation over here, when it was growth, we had 1 plus r in our parenthesis. So when we're looking for the rate, we kind of need to piece that apart and say, well, 1 plus what is 1.5? Well, we have 0.5 there. So 0.5 is going to be our rate, which is 50%. So that's how we kind of break that apart. Now this next one in my parenthesis, I have 0.75. So 0.75, hopefully everyone at home is going, well, that's less than 1. So that means I'm going to have a decay equation here. That's going to be getting smaller and smaller and smaller. And the factor is the entire parenthesis. So that's the easy part. We're going to just say 0.75 for my factor, and I'm done. Now the rate for this one, you got to kind of work backwards. And when we had decay, we used this equation. So 1 minus the rate is going to give me that factor. So I need to look back up here, and I'm going to say, well, 1 minus 0.75, or sorry, excuse me, 1 minus what equals 0.75? Well, 1 minus 0.25. So that's going to give me my rate, my decay rate of 0.25 or 25%. Now, last but not least, we've got one more example, and this is going to be a good one for when we talk about our word problem later when it's doubling. That will be helpful. So here I know right away I have a 2. That's definitely more than 1, so I definitely have a growth equation here. The factor is the easy part. That's just going to be 2. It's what's in the parentheses. And last but not least, we have rate. So to get the rate, I want to know 1 plus what equals 2. Well, 1 plus 1 is 2. So therefore, my rate is 1 or 100%. It should be a 0. This is tricky, guys. All right, so that is kind of breaking down the equations, and we can use what we just did there to write word problems, which I know we all love so much. I actually love these exponential growth and decay word problems. I think they're really applicable to things that happen in our lives, especially right now with this virus going on. A lot of you use that as an example. So hopefully you'll be able to look and apply it and see how it works in the real world. So I'm going to actually come over to my shower wall over here, breaks it up a little bit, add some color for you, and I think it's easier to read as I go along. So first I'll read the equation, sorry, the word problem. So right now I'm going to start with a dish that has 212 bacteria in it. The population of bacteria is growing by 80% every 2 days. So as always with word problems, I like to break it down before I even start it all. So I have a dish that has 212 bacteria in it. That's going to be my initial value. That's what I'm starting with. And it says the population of bacteria is growing. Grow is going to be a key word. Growing, it's going to be a growth, exponential growth problem here. It's growing by 80%, and it's growing every 2 days. So you're going to want to underline all your important information so you have it right out in front of you. And we're going to go ahead and start to write our equation out. So the first thing I'm going to do is I'm going to set up my y equals. Y equals, and I know that initial value there is going to be 212. We said we're starting with 212 bacteria. Now I need something in my parenthesis, and I know it's going to be to the power of x. This is always going to be an x up here. That's always going to stand for time interval. So we're going to be able to check at how many bacteria are over a certain amount of time. So that will stay x. Now the next thing I'm going to do is my rate. It's actually going to be easier to start with rate for these problems. And when we read the word problem, it said it's growing by 80%. So my 80% is actually going to be my rate, but I want to change it to a decimal form. So 80% is going to be 0.8 for my rate. Now that's not what's going to be in my parenthesis. Remember, the parenthesis is the entire factor. So with a growth problem, I'm adding. So I'm going to say, well, 1 plus 0.8 gives me 1.8. So 1.8 is going to be my factor, and I have written my equation. That's it, guys. Don't get too in your head about it. It's not too bad. Take it slow and kind of walk through it. I know it's a lot of new vocabulary that we're working with, but you guys can do it. So stick with me for applying now. Below we have, it says how many bacteria will be present in 4 days, 8 days, and 11 days. So I am not just going to use those numbers to plug into my x value. I need to kind of figure out what's going on here, because when we read the problem, it said the bacteria is growing by 80% every 2 days. So for x here, instead of, I'm not plugging in 4, if it's doubling every 2 days and I have 4 days to work with, well, 2 days can fit into 4 days 2 times. So I'm actually going to plug x into my equation here. And if you are using your phone, I'm also gonna, I'll also post a screen recording of how to use your calculator on your phone to work with these equations. So if I were to plug it into my equation, I would have y equals 212 times 1.8 to the power of 2. So that's what I would plug in. And if you're using your phone calculator, you're gonna wanna do 1.8 to the power of 2, and you can hit the equals. And then don't erase anything at all, just automatically right away hit times 212. And when you plug that in, you should end up on your calculator, and practice that. Don't just write this down, practice it with a calculator. You should end up with about 686.88 bacteria, about. You always want to label with your units. So for the next one, I have 8 days. We're not plugging in that 8 because it's we found out it's growing every 2 days. So how many sets of 2 days can fit into 8? Well, 4 of them. So my x is going to be 4. When you plug that 4 into your equation, into that x, you should end up in a calculator. And again, practice with the calculator to make sure you're typing it in correctly, and let me know if I can help you. For the amount of bacteria, you should have 2,225.49, about. And finally, for 11 days, this one's a little tricky. We cannot fit 2 days evenly into 11 days. So if I have sets of 2 days, that's going to fit into 11 days 5.5 times. Oh, switch my color on you guys. So my x is going to be 5.5. It's going to work in your calculator the same way. You're going to do 1.8 to the power of 5.5 and then multiply by 212. And you should end up with about 5,374, about. And I got 0.46. So that is our first application question. We're going to do 2 more together. And remember, if you still have questions, email me, send me a message on Remind. Go to those Zoom office hours on Tuesday, Thursday, or Friday. Okay, guys? The next problem that we have up is termites. So the house down the street from you has termites on the porch. The exterminator estimated that there are about 800,000 termites eating at the porch. Gross. He said that the treatment he put on the wood would kill 40% of the termites every day. So now I'm going to go back through and I'm going to underline like I did before. I want to pull out all of my important information. So I know we have termites. He's estimating there's about 800,000 of them. That's going to be our initial value. He said that the treatment he put on would kill. Kill is going to be a keyword there. If something is being killed, it's dying off, we're going to use our decay model here. And we have 40%. It's killing 40% of the termites every day. So I'm going to go ahead and start by writing my equation. I like to get the initial value out of the way right away. So I like to write out y equals, we said the initial value is the amount of termites to begin with. That was 800,000. We're going to figure out what's in my parenthesis in a minute, and it's always to the power of x. Now the rate for this one, it gives me 40%. They're being killed at a rate of 40% every day. Well, 40% in decimal form is 0.4. So when I figure out my factor with the decay model, I'm doing 1 minus. So 1 minus 0.4 leaves me with 0.6. 0.6 is going to be my factor, my decay factor here. So I can fill that back in my equation over here. And now I'm going to apply it and see how well the exterminator is doing killing these termites off every day. So for 3 days, this one's going to be easy. I'm talking daily. So how many times can 1 day fit into 3 days? My x value here is just going to be 3. So that one's not too bad. When I plug it in, it's going to be y equals 800,000 times 0.6 to the power of 3. So that one's not bad to kind of figure out what your x is going to be there. When you plug it into your calculator, you should end up with about 172,800 termites left after 3 days. So that was a significant decrease. For B, we want to know 36 hours. How many termites does the exterminator kill after 36 hours? Well, how many days can fit into 36 hours? So if I were to think this through, I'd say there's 24 hours in a day. So in 36 hours, there is 1.5 days. So my x is going to be 1.5. When I plug that into my equation, remember that x is the little exponent, and when you plug it into the calculator, you should end up with about, let me see, I actually didn't do this one out, so I don't have the answer for you right now, and I'm on my phone, so I don't have my calculator. Let me grab my graphing calculator. So when I do this one out, I end up with 0.6 to the power of, we said 1.5. And when I multiply it by 800,000, I end up with 371,806, we'll say 0.4, about termites left after a day and a half. So that's making sense. After a day and a half, I have this many left. After 3 days, it's going down even more. Now for 2 weeks, my x is going to be, we're going to say how many days can fit into 2 weeks? Well, 14 of them. 14 days in 2 weeks. So I'm going to plug in x for my exponent, 14 for my exponent, I should say. And when I plug that in the calculator, I did do this one, go me, I have about 626.9 termites left. And we have one more problem just to practice writing it out, and we'll go through 3 different time scenarios down here. Now we have mealworms. I remember doing that when I was a kid. Hopefully you guys got to do that in grade school too. It says in June, a 5th grade class started out with 10 mealworms for an experiment. So we're starting out with 10. That's going to be our initial. The population of worms will double, meaning it's growing by 100% every month. How many mealworms will the class have for their experiment in 3 months, 1 year, 45 days? So I'm going to go back and say every month. That's going to be our time that we're looking at. So again, I like to start by just putting my initial value out. That's the first thing I like to do. So y equals, we said the initial value is going to be 10. We'll figure out our parenthesis in a second, and it's to the power of x. Now my rate here is 100%. It gives it to me. So I have 100% for my rate. In decimal form or whole number form, that's just 1. So now my factor, I know with growth I'm doing 1 plus the rate. Well, 1 plus my rate is 1 plus 1 which is 2. 2 is going to be my factor. The factor is what goes in that parenthesis here. So now I'm going to go ahead and figure out what is happening for A, B, and C with these specific time periods. So for A, it says 3 months, and it tells me that we are growing every month. So this one's going to be easy, kind of like A in the top one, right? We're still in the same unit. We're both in months, and my X here is just going to be 3. Now when I plug that into a calculator, out pops 80. Now hopefully that should make sense. If you think through this problem, this is one where you can go back and ask yourself that question, does that make sense? Because sometimes maybe finding the equation is a little bit hard, but if you kind of walk yourself through it and you say, well, I'm starting with 10 mealworms, right? It gave me that. And if it doubles, I have 20. And if 20 doubles, and this is what we're initial, if 20 doubles, I have 40. And if 40 doubles, I have 80. So in that 3rd month, after my initial, I do have 80 mealworms. So that was just a quick check that you can kind of do off to the side. Now that's not going to be fun to do when we get bigger numbers like this. So you can work with the smaller numbers to see if you got it right, and then use your equation to apply to the bigger numbers. So for 1 year, I have, how many months can fit into 1 year? Well, 12 of them can. So my X is going to be 12. And when I plug that into my calculator, I end up with 40,960. 40,960. And again, you're going to do 2 to the power of 12, and then you're going to hit equals and push times 10. I'm going to, again, I'll put a screen recording of how I'm doing that on my calculator so you can figure it out on yours. And now for 45 days, last but not least, and then we will be done. For 45 days, I'm looking to break that into months. Well, 45 days is equal to 1.5 months. About, if we said a month is 30 days. So we'll say about 1.5 months. And when I plug that into my calculator, I'm left with about 28 mealworms. I think it was 28.28, and I felt bad giving part of a mealworm, so I just said about 28. So that is it for exponential growth and decay. Again, I'm aware it's a lot. That was a lot to kind of squeeze into a 20-minute video. If you have questions, please reach out. If you don't see the Zoom code, please reach out. Let me know. I am here to help you, and we will get through this together. I will see you guys hopefully tomorrow on Zoom. Talk to you later. Bye-bye.